In the previous lecture, we were discussing about some of the physical features of turbulent flow. Now, the question is, how do we represent those physical features or take those physical features into account through a mathematical approach. Now, it is very difficult to have a rigorous mathematical approach for turbulent flow, because you have a wide range of length scales and time scales, that is one of the physical features. So, if you want to computationally solve a problem, you may need to resolve a domain which should be able to capture from the smallest, that is the molecular scale, up to the large eddy scale, all the relevant spatial and temporal scales. This being easily said, but it is not so easy to implement it, because it requires huge computational effort. There are established strategies known as direct numerical simulation strategies, through which the Navier-Stokes equation can directly be used to solve turbulent flow problems. Then remember that Navier-Stokes equations are very much valid for turbulent flow, provided other conditions are satisfied. It is a question of implementing the numerical scheme that makes it so challenging, and certain statistically based models have come up which hold the capability of solving turbulent flow problems in an approximate sense which serves most of the engineering purposes. So, we will now discuss about the statistical treatment of turbulent flows. So, let us say that there is a powerful probe or a device which is plotting one component of the velocity. Remember, a turbulent flow, because of its random fluctuations over space and time, is always 3 dimensional and unsteady. There is nothing called as steady turbulence, it is a misnomer. I will tell you later on that what we mean as steady turbulence in terms of the physical understanding, but the terminology is not very appropriate according to my consideration. So, we make these two plots for two different scenarios. In one case, the plot is like this. In another case, the plot is like this. So, these representations are very difficult to vividly capture through a model, because you see that there are such small oscillations of u over time. Similarly, if you draw a variation of u over space, similar things can be inferred. So, now what you can do is that you can make a statistical average of this. How do you define the statistical average? You define u bar as this. So, what is this? So, essentially you are integrating u over time. It could be u, v, w, p, any variable. So, you integrate this over time from 0 to a time period t which tends to infinity. Now this has to be clearly understood, this does not literally mean infinity. What it means is that it is significantly larger as compared to these small fluctuation times. The time over which it is fluctuating, this capital T must be significantly larger as compared to that. So if that be the case, then you can smoothen out this data in terms of an average, and the u bar may be something like this. Remember, this t has to be much larger than the small fluctuation time scale, but it also has to be smaller than the total time, otherwise it cannot capture this variation of the average over time. Okay. Here if you make an average, the average u bar may not vary with time, although u varies with time, but u bar is not varying with time, and this is called as stationary turbulence, which sometimes is erroneously called as steady turbulence. So just like how this is called as time averaging, similarly this averaging can be done over space. Instead of u integrated with respect to time, this is u at a given location. You could integrate u over space at a given time, and there that will be called as space average. So I am not putting any bias, this is just the standard way of calculating the average, no matter whether it is time average or space average, the concept remains similar. So then if you have a function f which may be u, v, w, p, whatever, it can be resolved in terms of average and the fluctuation. So the difference between u and u bar, for example, is u prime. So this is called as Reynolds decomposition. So now if you take average of both sides, f bar is equal to average of f bar, which is f bar itself, plus average of f prime. This means average of f prime is 0. Okay. But the interesting thing is that although average of f prime is 0, average of another function g prime is 0, average of the product f prime g prime, this is not equal to 0. The reason is that they individually average to 0, but their products when averaged, there is no guarantee that that will be 0. So with this little bit of background on the statistics of turbulent flow, so we will define maybe a few other important terminologies. For example, RMS, say RMS of u, or root mean square. So RMS is basically u minus u bar square of this, and then so this is not 0 definitely. Okay. So now we can formulate the Navier-Stokes equation by decomposing it into the mean and the fluctuating component, and this is called as Reynolds averaging of the Navier-Stokes equation. The advantage with the Reynolds averaging is that you are not required anymore to capture the smallest length scales and smallest time scales. So you can consider a length scale and time scale which is substantially elevated as compared to the finest ones which are physically there, so that computationally the problem becomes more tractable. So, we will write the Navier-Stokes equation in the conservative form. There may be a body force, maybe let us write it, but the important thing that I want to infer from here will not depend so much on the body force. So, what we do is that we write this, we break this up into ui bar plus ui prime. So, this will be ui bar plus ui prime, this will be uj bar plus uj prime, this will be p bar plus p prime, this is ui bar plus ui prime. Okay. So, then when you do that, the next step is that we will do an averaging of this equation, put a bar at the top of all the terms. Okay. If you do that, what will be the result of this? So, another important point which I have missed, ideally you should resolve also rho equal to rho bar plus rho prime, because density may also be fluctuating in a turbulent flow. But if you assume a constant density flow, that is what we are doing. Remember, not for all cases we can do that. If it is not, then or better to say, for our interest it is non fluctuating. It may have a larger time scale over which it varies, still it is okay, but it is not fluctuating like the other parameters u, v, p. So, if that be the case, then here, so if you take the average of this u prime will be 0, so it will be del t of right. So, remember that the time scale over which you are finding out this average is different from this one. So, this time derivative and the time averaging, they do not conflict with each other. This term is a little bit special one, so we will take it up later on. So, this will be minus and this will be so, if you do that, this term remains, right, this term has to be worked out. So, let us write this one ui bar plus ui prime into uj bar plus uj prime, average of that. Okay. Now, ui bar uj bar product of that is fine, ui bar into uj prime average, ui bar being a constant with respect to the average will come out of the averaging and it will be integral of uj prime over the time period. So, that will be 0. Similarly, ui prime into uj bar being a constant will come out of the integration and ui prime integrated over time will be 0, but the product of fluctuations that will not be 0 on an average. So, this will be so you can in principle write a Reynolds average Navier-Stokes equation or RANS as it is called, which will be okay. So, this looks like the Navier-Stokes equation in an unaveraged sense except for this additional term. This term exactly because of the dimensional equivalence with this term is called as Reynolds stress or turbulent stress. Not the whole term, only the term in the bracket, right, because this is the standard tau ij. So, we can write this as plus with a minus we can put inside this term. This is the Reynolds stress. Okay. Okay. So, this is purely from the analogy of the dimension of this with the dimension of this. So, question is that while trying to get rid of the problem of solving a turbulent flow, we have come up with a situation where we have incurred some additional unknowns which are these ones, and that will be a second order stress tensor. So, one possibility is that instead of writing this minus rho ui prime uj prime average as it is, you define this in terms of a fuzzy parameter which is called as turbulent viscosity, which is not a constant but a parameter which depends on the turbulent fluctuations which can be mathematically modeled. So, this is not a constant, but this needs to be closed with the aid of other turbulence parameters. This is called a closure problem in turbulence modeling, that the Navier-Stokes equations after Reynolds averaging does not remain closed because of the introduction of the turbulent stress, and you need a closure model for this mu t which is called as the turbulent viscosity to close this. So, I will talk about certain models which achieve this, but before that I will try to discuss some special cases of the statistical approach. Number one is homogeneous turbulence. Homogeneous turbulence is a case where the turbulent statistics, that is for example average, RMS, etc., these are not functions of position, right. Homogeneous term we have already discussed, but homogeneous turbulence only talks about the homogeneity in the statistical representation, not the homogeneity in the parameters, because parameters are all distributed over position. Then isotropic turbulence. So homogeneous turbulence means that the turbulent properties are not dependent on position, which means that they are invariant to translation of coordinate axis, because you can change the position by translating the coordinate axis. So this is translation invariance. Similarly, isotropic turbulence talks about rotational invariance. Not only that, by definition it is invariance with respect to translation, and that is how it is defined, plus reflection, all sorts of these transformations which preserve the length. So it is, the statistics are invariant with respect to that. So isotropic turbulence by definition must be homogeneous, right, because there is a translational invariance associated with it. Now these types are important because you can conclude something about the averaging technique. In real experiments we neither purposefully do time averaging nor we purposefully do space averaging. What we do is called as ensemble averaging. So what is ensemble averaging? That you do a large number of repeated experiments under identical conditions. This is very important, that you do a large number of repeated experiments under identical conditions. So if you repeat the experiments under identical conditions, then that average is called as ensemble average. If it is a homogeneous turbulence, then you can say that ensemble average is same as space average, right, because it does not vary with space. So repeating it at different spatial locations is as good as repeating the experiment under identical conditions. Similarly, if you have stationary turbulence, you have ensemble average equal to time average, because things do not vary with, the turbulent statistics do not vary with time. So if you have homogeneous plus stationary turbulence, that will mean that time average equal to space average equal to ensemble average, right. This is known as ergodic hypothesis. So if this ergodic hypothesis is satisfied, the averaging that you put in this equation, it could be time average, space average, ensemble average, whatever it is. So now we will discuss a little bit about this closure model, that how you can close this system of equations. So I will talk about one classical model which is called as Prandtl's mixing length model. So purely from dimensional arguments and by drawing analogy from the molecular theory, Prandtl proposed that the kinematic viscosity can be thought of as a product of a length scale over which there is turbulent mixing times the fluctuation component of the velocity. So this is meter, this is meter per second, product is meter square per second. So this is nu t, which is this mu t by rho, okay. Problem is you neither know this nor you know this. So you can, for example, have a different way of looking into it. For example, you could have u prime So, this is the gradient of the average times the mixing length. So, if you do that, then this will be so this y is basically the direction in which the mixing takes place. Okay. Let us say you have some eddies interacting with another set of eddies. There is a fluctuating velocity because of which in the y direction, because of which this set of eddies is interacting with this set. If this is moving slower, it will try to slow this down. So, that mixing length can be modeled in this way. So, the kinematic viscosity can be expressed in terms of a mixing length. If this mixing length can be somehow estimated, then you can close this. There are various other closure models, like you can calculate the turbulent kinetic energy, which is the kinetic energy calculated based on the fluctuating components of velocity. You can calculate the dissipation rate of kinetic energy, which is the epsilon that we have talked about, and you can have two additional equations on k and epsilon, which will be, then you can relate this mu t with k and epsilon, that is called as k epsilon model. So, there are various models. This is not a course on turbulence modeling, but I am trying to give you the philosophy. The philosophy is that you have to somehow close this, you have to somehow get an expression for this in terms of other parameters. Okay. So, this is a single parameter. So, now you have only one parameter for which, using which you can close this system. Now, so far so good, but there is one very important issue, that no matter whether the flow is laminar or turbulent, very close to the wall it is always laminar. So, wall bounded turbulent flows are very important, and we will discuss briefly about that. So, let us say that you have this as the wall and this as your y direction. So, you can write tau wall is equal to mu du dy. So, you can very close to the wall you can write this. This is called as the near wall behavior in the viscous sublayer regime. In some books it is called as a laminar sublayer. It is not correct, because in the viscous layer where the flow is predominantly laminar, but there are some small turbulent fluctuations in that layer also. That does not affect this wall shear stress much. So, we can write in this way. So, this tau wall you can write in terms of a velocity scale rho into u tau square. This is just from dimensional analogy. So, u bar by u tau is equal to, you can write rho u tau y by mu, right. So, this is y by a length scale mu by rho u tau. So, this is defined as something called as u plus, and this is defined as something called as y plus. Okay. So, very adjacent to the wall you have u plus equal to y plus. Of course, after you go a little bit away from the wall you will have u plus as a different function of y plus, but when you go to the outside far away, little bit away from the wall, the turbulent stresses will come into the picture. So, this is like the inner behavior. The outer layer behavior is given by this is called as velocity defect law. These are all from dimensional arguments. Okay. So, this is called as the velocity defect law, and I will show you later on that where from this velocity defect I mean how these two laws correlate. So, this is a inner behavior, this is an outer behavior. There is this deviation of u bar from the free stream is because of the turbulent stress, and that is somehow normalized with respect to u tau, and that is how the inner layer effect propagates to the outer layer. So, this is a function of eta, where eta is a different dimensionless scale y by delta. This delta is a length scale of the outer layer. So, this has nothing to do with the inner layer. So, now you have a continuity of du dy of the inner okay. So, you can write, so du dy will be continuous. So, you have u tau, so this is du dy is rho u tau square by mu. So, or you can write it in another way, du dy plus into dy plus dy, dy plus dy is rho u tau by mu. And this is du bar d eta into d eta dy, d eta dy is 1 by delta. Okay. So, now we play a simple trick, we multiply both sides by y. If we multiply both sides by y, this becomes y plus and this becomes eta. So, y plus du by dy plus becomes eta du d eta, where these two laws overlap. So, this is about the overlapping region. So, that means this is a function of y plus only which does not understand eta, and this is a function of eta only which does not understand y plus, that means each is a constant. So, if you integrate it, so this is this is right, this is du plus dy bar into there will be a u, another u tau. So, this will be, just we change it to u plus in place of u bar. So, we can do it because both sides the definition of u bar is the same. So, we just switch from u bar to u plus for our understanding, because we have used here y plus. So, here we will use u plus. So, here it was u bar, here also u bar, change both to u plus by multiplying the same factor in the both sides. So, if you now integrate this, you will get u plus is equal to a constant dy plus by y plus will be ln y plus a constant of integration. This is called as logarithmic law or the log law. Remarkably, this 1 by kappa, it is a universal constant, and this kappa is called as von Karman constant. So, this for all experiments this has been found to be around 2.5. It is remarkable, but experiments have revealed that, and this is about 5. So, these are universal constants. So, now if you can sum up this u plus with ln y plus, so because it is a logarithmic graph, so you will have first this kind of a variation, then so you have about y plus equal to 5, within which you have the viscous layer where you have u plus equal to y plus, then it will be a different function of y plus, not u plus equal to y plus. So, up to a limit of 30 you will still have this behavior. Then in the outer layer you have this logarithmic law, u plus is equal to 1 by kappa ln y plus b, means in the u plus versus ln y plus it will be a straight line, right. So, it will be a straight line like this. So, if you plot real physical data, they will smoothly converge from here to here, and then the real data beyond some y plus will have a significant deviation from this behavior. So, then this layer is called as viscous layer, this layer is called as buffer layer, and up to this is called as inner layer, and there is a overlap between the inner and the outer layer. So, this is the outer layer, see the definitions. So, you can relate that with this one. So, this is the overlapping region where the log law holds, the overlap between the inner and the outer layer, and here the experimental data will be like this. So, this yellow is the experimental data, red is the fitted law, and you see that how remarkably the near wall behavior varies under certain conditions. So, we have discussed the fundamental aspects of turbulent flow in the last two lectures. There are many practical engineering applications where the concept of turbulent flow and laminar flow, a combination of these is used to design a body for minimizing the drag forces. So, we will have a separate tutorial for you where we will expose you with the practical considerations for designing of, for example, aerospace vehicles or design of any engineering object by minimizing the drag force based on the concepts of laminar and turbulent flow that we have learned by this time. Thank you very much.